Hi everyone. Thanks for coming to this talk. Today we're going to dive into the philosophies and reasons why we're doing what we're doing, right? And this becomes quite interesting when you start the train of thought. And I hope that it gives some new insights. So a little bit about me. I'm Lucas. At the moment studying, just started my master's studies in Helsinki, in Finland. But studying is mostly kind of one thing I do for fun. Before this, I worked 5 years for WeWorks startup and been speaking at many KubeCons and so on because I've been a Kubernetes maintainer. Now these days I research all kinds of interesting things. Now at the moment, databases, access control, graphs, all kinds of things. So yes, and also stuff with in the university. Anyways, what are we going to talk about today? First, we're going to take a look at the complexities of database administration. A subject which should be quite familiar in this kind of conference. Then we're going to look at how Kubernetes solves these kind of problems in a generic way, and why that is the operator, right? And of course, because this is a TiDB conference, then we're also going to take the practical example of TiDB operator, which I've investigated quite a lot recent weeks. And then I would have liked to do the demo, but I only have 30 minutes, and the upgrade takes 15 or something like that, so it wouldn't leave me with almost any time to actually talk about what I'm doing first. But we'll see some screenshots, and if you want to see it, I can show it afterwards. So we are here at this conference because we are interested in the intersection of the transactional and the analytical processing stuff. But this puts some quite tight requirements on what a solution we can have. So when we want to have a fault tolerance and also a lot of capacity in the system, we cannot go with only one node. Okay. Well, we cannot go with only one node anymore. In terms of physical, we need some consistency protocol. Consistency protocol in turn gives us some quite other interesting problems, and also we start needing sharding, all kinds of replications, and so on and so forth. This is something that's been studied quite a lot both in academia and industry, and there is no easy solution. So we wanted something which ends up giving us something complex, because when we have multiple nodes, we need, as system administrators of this system, some pretty advanced, in most cases, scheduling logic. We need to take care, because of the consensus algorithm, we need to take care when upgrading or scaling. So to scale out, we cannot just add a new replica and without having some kind of learner phase, kind of replicating the new data, figuring all that out. How long is it going to take? How does it impact the system? All of these kind of things. We need to have some learner mode. We cannot just kill the consensus leader like that and without giving it a handoff. All of these kind of things. When we, this is just not a comprehensive list, just to kind of showcase that there are complexities with operating this kind of distributed system. And yeah, sharding. When we don't have all the data on one node, then we need to figure out where it is, etc. Essentially, it's a lot of work for the sysadmins. The conclusion here, kind of as a general takeaway, is that operating something non-trivial is a non-trivial task, which sounds quite obvious, but for most of the people, this is kind of the day-to-day life, right? We started off here, then we're all happy. We have, the team of this amount of resources, and then business says, oh, we need to scale. And then the complexity of our thing goes to the roof without us having any more resources than we had before. And actually, this is when you start looking for these things in different places, we find that this is a very generic problem. And we want to find some generic solutions to this. So what does Kubernetes do to help us with these kind of things? Well, Kubernetes, if you don't know about it, is an open source container orchestration system. It's created by Google in almost a decade ago already. And it aims to simplify or solve the sysadmin operation challenges with regards to application orchestration. Now, the applications just happen to be in containers. That is more a coincidence than a, a requirement. It is part of the Cloud Native Computing Foundation, for which I'm an ambassador as well. And I was one of the maintainers, but today we have more than 80,000 contributors, so it's a huge project. In fact, one of the world's largest, top 3 or 5, depending how you count. It runs on all of the in all environments, from cloud to on-premise, and my first contribution to it was to make it work on Raspberry Pis as well. So you can you can put them in really small places. And it literally you can configure everything. And I think one of the interesting things looking at the TiDB talks here as well has been that name any tuning problem a customer might have, and there's a flag for that in TiDB or TiKV, right? Kubernetes is the same. Like you can customize almost anything inside of the system. There's hundreds and hundreds of config parameters, tens, 20 different extension mechanisms, and so on and so forth. So you can go really kind of make it your own. And as I said, it's based on decades of experience inside of Google. They published these 2 papers, about Borg and Omega, in which they detail why they did certain things the way they did, and also they talked about the stuff that they didn't do so well, and they wanted to change for the next version. And on a high level, it looks like this. So I'm a user. I want to run an application. I tell Kubernetes that I want to have this application run in production. This REST API server is completely stateless. So when I tell I want to have 3 Nginx web servers, the API server just stores this in a replicated etcd cluster. And if there would be nothing here and nothing here, nothing would happen. It's just a dumb API server that stores some key value pairs in a key value database. But once we add these kind of controllers on the side here, then stuff starts happening. Especially when we add nodes to this system. The nodes also they look in the API that what should I do, and kind of make those things happen. And this design mechanism is quite interesting, as we will see. So it's a control plane for almost any infrastructure, because it's a set of automated controllers. There's 45 in them. I counted the last version of Kubernetes. So like when you install the system, you could actually have it's smashed into one binary, but you could technically have 45 different binaries doing 45 different things. Anyways, these controllers are kind of very do one thing Unix style, do one thing and one thing well. So a set of these, they collaborate and add some kind of operational knowledge on how to do a certain thing, X, in production. So for example, there's one controller that knows that I know exactly how to take a set of nodes and a set of workloads and map them together. There's one controller that's only for that. That's called a scheduler. There's one controller that is looking all the time at the workloads, and then it looks at, oh, this workload is actually running on a node that hasn't posted a kind of health check in 10 minutes. It must have died. So now I need to replace this workload to somewhere else. And other things that, us sysadmins used to do, right? In the previous life before Kubernetes, these are all things that someone had to kind of configure manually and kind of figure out and based on experience. So kind of a lot of heuristics about how to operate a system, they have now encoded inside of these controllers. So these controllers know how to operate some kind of external system. These are well, Docker is one of the most obvious ones, but then there's a lot of interfaces here. So like, is it storage, or is it networking, or is it containers or VMs or whatever, cloud APIs, it can be anything. And one of the key findings in the Borg and Omega papers from Google was the kind of this control by choreography. And that means that essentially we have all of these small things that do only one thing, very, very kind of one simple thing, and they do that well, and together they form up a pretty large, extensive system. So this controller-centric model lies at the very heart of Kubernetes, and it's what kind of makes things in Kubernetes happen. But why did they choose a controller-centric model? Like on the market, let's say it like this, on the market when Kubernetes was released, there was no controllers. So we had Ansible and similar systems that you could do some kind of scripts, and often, in the best case, you made them declarative, that you actually checked that what is the actual state before modifying anything. But a lot of the bash scripts that most people do is just they just run actions here and there, and then you need to execute them manually. So when you deploy, then you run the script, but then during a week until you deploy the next time, nothing happens, and there's chance for errors. And why they chose a controller-centric model is because chaos is inevitable. And anybody knows this, that at least has a working desk or, I don't know, kitchen or something else. It always ends up messy after some time. What they also found in the paper is that failure is the norm. That even though we deploy, say we run the Ansible script, it does some things somewhere, and then we leave it be, we don't check the state or anything for a week until we deploy next time. During that week period of time, anything can happen, right? There can be nodes crashing, there can be DDoS attacks, there can be anything in this system. And, RAM burns down and whatever. So this is something you need to take into account. On a very generalized model, you can look at it like this. So we start by order. When we deploy something, when we buy a server or something like that, we have total order. And then over time, it just gets worse. This is the second law of thermodynamics. Everything in the universe becomes more messy over time. I mean, it's a law of the universe. What can we do about it? Well, we can reverse the process, but it requires energy, right? So we need to do a conscious effort to fight this kind of inevitable flow of the universe. So before lunch, you have clean dishes. After you've eaten lunch, messy dishes, you actually need to expend energy and effort into that. And otherwise, your kitchen will be infinitely messy, right? Kubernetes is very much the same thing. You buy a computer, you spin up a cloud VM or something, everything is perfect order, you set it up, configure it. Then, a week in production and the system looks like this. So we need something to kind of fight that inevitable cause of our systems. That is why they chose a controller-centric model. But now we had this kind of very linear and nicely looking axis here, order and chaos. But what are those? Well, first we need to know what is declarative and what is imperative. So declarative are states that we can define as points somewhere. If we think about it in an abstract manner, it is what we want. What is the thing that we are looking for? That is the declarative state. How we get from one declarative state to another, how we get from one point to another, there can be many such paths, right? So this is quite obvious, but it is not obvious in the sense that for programmers at least, we always tend to think that we will always go direct here. And it will always work, right? In real systems, though, it usually goes somewhere here, and then we shoot there, and then we compensate there, and then it goes like all the way. We never might even hit the target. In the thesis I wrote about this, I now can't remember, was it Twitter's infrastructure or something, like they always see, or in any large enough system, you will always have errors. You will never ever hit that exact point you want to be at, because the rate of errors is much faster than what you even can repair. So, but just by defining that, you don't define the actions that you want to happen in your system. Like, you don't just run that script, because there's no sysadmin that can type that fast when you get a sufficiently large system. So you instead need to say that I am here, yes, but I want to be there. And then you make a system that step by step goes towards that state. And this is really important, because if you don't know, like, most systems never define this place. Most systems just shoot an arrow towards this side and hope that we end up in the right place. That is bash script. But here we actually say that we want to be exactly at this place, exactly at this point. And this is how to get there. Because if we don't, anything we do, any error, that is correct operation by the system. So the kind of key takeaway is that systems get less ordered over time. And we need to do periodic corrective actions. And what is interval is really dependent. Kubernetes, most controllers, they check every 30 seconds that things are okay, because the rate of errors in huge computer systems are quite massive. But for something that changes less frequently, it can also be an hour, a day, or something like that. But it always we always need to know that what is our guiding star, right? Where do we go? So that is the declarative desired state. So this is popularized as operators. Okay. So in 2016, I think it was at the Seattle KubeCon, yes, in November, Brandon Phillips, back then at CoreOS, coined operators, the framework. And Kubernetes made this possible because of its design. And in fact, Kubernetes is just a set of these operators, right? But he coined the word and showed a TD operator as the first operator. And it's a set of these reconcile loops that build in these kind of sysadmin best practices. What would a sysadmin do, and write that in code. And why do we do this? Well, we delegate repetitive human activities that are devoid of lasting value. So like everything that we don't want to do ourselves, we just automate, right? We put in the operator, it's once done, then it's done. Then we just run it. So what does the operator, or what should it do? It should keep infrastructure in control. So always minimizing, so I am here, but I want to be here. Then I take a step here. And then always, but this kind of can change over time as well. So we're always chasing a moving target. So we minimize the drift. We want to get resource scalability so that we kind of can, well, for example, in TiDB operator case, we can have multiple TiDB clusters within the same Kubernetes installation, for example. Bin pack them real hard. We want to have monitoring scalability. We want to get the high value signals of like how is the cluster doing, the aggregated metrics. And for example, you can do stuff like auto scaling, auto failover, these kind of things. based on these declarative rules. So for example, you might say that if it's always at 90% CPU, the TiDB or TiKV thing, well then scale out. Those are the kind of policies we can start defining. So we don't have to be pinged at every time threshold goes over and just bump the thing. Then knowledge scalability as well. As people in your organization change, if there is a definitive guide of like, these are the steps on how to operate this system X, by looking at the code of the operator, then there you have your documentation. Of course, there should be other documentation as well, but that is the definite truth on how to operate this kind of system. So we get all kinds of scalability kind of factors, dimensions in this, with this thing. So it's kind of like a, what do I say, industrial revolution, you could think of, so that we are not the ones that are operating the machines anymore directly. We just don't have cognitive capacity for that anymore. Our systems are sufficiently huge these days that we can't just cope with that. Instead, we make some automation that operates the machines. And with everything, like as systems get bigger, as there's more AI things and all of these are just gonna increase. So here, that was kind of a fast introduction of operators as is. Then what is the case with TiDB operator? So it essentially provides you with this declarative desired state. So like you get to specify exactly how do you like your cluster. So you get also, in the same way as you would to some cloud, it's self-service in the manner that you just tell the cloud that I want a virtual machine exactly like this and exactly like this. You also specify to TiDB operator that exactly this kind of cluster I would like to have running now with TiDB version this and that, configuration this and that. And then we get all of these kind of benefits because someone that has been writing this TiDB operator, they know how to operate TiDB. Perfect. Then I don't need to know how exactly to do an upgrade, for example. But I know that when I'm changing the parameter that I'm going from this to that version, then it will do it for me. It will do all of the kind of getting back what we talked about in the beginning, like raft logs, kind of take graceful deletion, all of these kind of things. Like it looks at the metrics, it kind of checks it out, make sure it's safe to upgrade, for example, before we can do all of that kind of stuff. I don't need to know about. I just tell that these are the things I want. So we get all of these kind of features built in, and how it works on a high level is that we have some desired state source. And this is a Kubernetes API to which we tell that it's called a custom resource, that we make a JSON file, we send it to the API server. And from there, the operator takes the definition, and then it also starts sending TiDB some requests and like, how are you doing? Like, what is your state? Check the PD, all of that kind of stuff. From there, it gathers up information, and it sees that, oh, actually, my version is too old now. User has said that I want to have 7.1.1, but when I observe the target system, that's 7.1.0. Okay, I need to do something. So I make a plan, and then I say I will need to upgrade the target system to 7.1.1. He goes ahead and does that, and then at the end of the day, it might work, it might not. So say that there was no such, like, or there was some problem with the upgrade, then we tell that to the user and then send the actual state now. Like, yeah, we're still at 7.1.0, but there's a reason we didn't upgrade because it wasn't safe, for example. And then when it has done one of these loops, then it just goes and does the same thing. So it's gonna over and over and over infinitely many times. It constantly keeps doing this. Always checking, am I in the place that I need to be? Let's see. How much? Yes. So the demo I did with this was to have 9 cloud VMs, 3 each for PD, TiDB, TiKV. I installed the TiDB operator through the GitOps engine. I set up the monitoring stack. I created one of these kind of desired specifications that I want a TiDB with this exact specification. And then in this, I specified some topology things and upgrade tuning. And the demo I was running is running on UpCloud, one of the Finnish cloud providers. So that was nice to, thanks to UpCloud for donating the resources for this demo. What I'm doing in this short demo is to upgrade exactly from 7.10 to 7.11. I don't know how to operate TiDB, but luckily this operator knows how to do it. So it will upgrade the TiDB cluster gracefully while serving at the same time 60,000 requests per second. And the demo manages to observe no reconnects even while this update is. So we're constantly at 60,000 requests per second. User doesn't even notice that we upgraded the cluster in between. And I didn't need to know even how to do it. While monitoring the TiDB performance every 15 seconds, we gather the metrics, get them to a Grafana dashboard. So essentially, I go and I have everything in GitHub, the declarative state, that what is my leading star. That is in GitHub. I have this Flux. So I worked for WeWorks. 5 years they made this. It's a CNCF project. It essentially does a git pull and applies to Kubernetes. TiDB operator notices that I'm not running the right version. I'm running an older version than I should be, according to the user. It starts modifying kind of the Kubernetes state. It says that I need to upgrade this, I need to upgrade PD, TiKV, TiDB. When it tells that to Kubernetes, the Kubernetes controllers start changing the workloads. When they start changing the workloads, the node agent sees that, oh, I need to run a new container, I need to kill the old one. And so on and so forth. So what I did was to go into my GitHub, I changed this one value. And then I just wait 15 minutes or something, and that's it. So let's look at the stats. So here we can quite nicely see that I have 3 TiKV running. First, it kills this one, goes down to 0. That leads to some of the other nodes compensating because of that. But then it kills them in order until they are all upgraded. The CPU usage tells the same story. I/O, same thing. Same thing for storage, one by one. And it did so gracefully because we were still able to handle all of the requests. So here is the command per second, around 60,000, no problem. Also TiDB was upgraded in the same way. It uses some pretty clever Kubernetes tricks under the hood. So essentially it first removes the endpoint so no new requests are added, then TiDB handles all of the requests that it needs to, and first then it's killed. And as was mentioned in the LinkedIn talk, yes, there is 10%-ish degradation while there's one less replica. But that is, you will see less of that the more replicas you have, and also it's by far reasonable. So what didn't I have to do? The only thing I did was change one value in GitHub, right? So I didn't have to do any manual service recovery, no TLS setup, no scaling, version upgrades, reconfiguration, all of this. It's all handled for me. So when I don't have to do 102 or 1002 commands to upgrade this anymore, it feels kind of nice. And this is one example of how we go from the place where we need to operate all of the machines directly. I'm not that fast at typing, so I could do any larger system, handle any larger system which has a constant rate of errors. So instead, I start putting my effort into writing the operators in this way, and then I have a scalable system in all kinds of ways. So further reading, well, I wrote a thesis about this, bachelor thesis, a couple of years back. There's some other good talks on control theory, from which all of this kind of stems. The disciplines, there's some good things from his theory, control theory, lots of other information theory are related. But yeah, that's it. Thanks.